This is Group 161, and our project is voice-based medical condition recognition, leveraging audio descriptions for ailment identification. Now, come to the introduction. Imagine living in a remote village with limited access to healthcare facilities, and imagine falling ill and struggling to convey your symptoms over the phone to a healthcare official, where who might be hundreds of miles away. This scenario is a reality in many rural areas, and this has been a big problem in all over the world. And to tackle these challenges, we came up with a project where it takes in audio descriptions from the patients and classifies them into medical ailments so that the healthcare officials can identify the symptoms of the patient and provide proper healthcare. Our system employs audio to text conversion technology, which transcribes the audio recordings provided by the patients describing the symptoms. The transcribed data then undergoes rigorous analysis, employing advanced neural network techniques such as transformers to identify and classify potential medical ailments. Our dataset consists of thousands of audio recordings of common medical symptoms by, by various individuals, various patients, and we have partitioned the data into train, test, and validation sets using a 80-10-10 ratio. Coming to the baseline model, our goal was to classify the medical ailments by converting the audio into spectrograms and using a CNN model to classify them into different medical ailments. The model that we used was based on transfer learning using ResNet 50 architecture, which was pre-trained on ImageNet, and we have replaced the final layers of the model with custom layers for medical ailment classification. Coming to the training of our model, initially we train the model for 10 cycles and then we unfroze the layers, we unfroze the learning of the model and fed it for 50 cycles. We used learning rate finder to find the optimal learning rate for the training, and the we also visualized the plot for learning rate so we get the optimized learning rate. And for evaluation, we used accuracy. These were the parameters of our model. We used a pre-trained CNN model, ResNet 50, and we also used data augmentation to provide to get more patterns from the data, and we used learning rate finder to get the best learning rate. And with our baseline, we got an accuracy of 31.45. And as you can see from the graph below, we found the uh, the accurate learning rate using the learning rate finder. And on the right, there's a confusion matrix of the classification provided by the model. Coming to our main model, in order to enhance our success rate in categorizing the data, we substituted our input with transcript text instead of spectrograms we got from the audio files. We used sentence transformers to encode the text input into numerical representation, and then we fed them into a dense layer neural network for classification. And coming to our architecture, the input layer receives the encoded text, followed by a dense layer which has 1024 neurons, and uh, a, with a ReLU activation function. And our output layer is also a dense layer with softmax activation function. And this is our implementation where we trained the dense layers open, and we kept the sentence transformers frozen, and then we unfroze the sentence transformer model, and and the whole model was fine-tuned, and we trained it for 50 epochs. Our evaluation metric was test accuracy. These were the model parameters where we used a pre-trained sentence transform model, bird-based, and the activation functions, ReLU and softmax. We used categorical cross entropy as our loss function, and the optimizer was Adam, and we trained it for 50 epochs. Coming to the result, We got an accuracy of 72.11, which is a significant improvement from the baseline model where we got 31%. And you can even see the confusion matrix, which seems to be more better than what we saw from the baseline. And coming to the future scope of our project, we plan to extend the model to recognize symptoms in multiple languages, and we also try to integrate real-time symptom recognition and come to the continuous learning so that the model will evaluate the evolve over the time. And we also would like to have a wearable device integration so that the patients can do it anytime. And the last thing was privacy preserving solutions so that the patient data will be preserved. Thank you.